Okay, great. So today at our survey lectures, we're happy to have Maissam Barkeshli from Meta and University of Maryland talking about sharpness dynamics and neural network training. Go
Hey
for it.
guys. Hi Jim. Okay, thanks, Surya. Thank you all for coming. Yeah, so I've actually been on leave at Meta Fair as a visiting researcher since January. The things that I'm going to be presenting though are works that we actually completed before I joined Fair. So hopefully maybe in the next meeting I can talk about some newer stuff. I'm going to be basically covering three sets of works. With all of them are with my graduate student Dayal Kalra, and Tianyu, who is Andre's student, joined us for one of the projects. But these guys did all of the numerical experiments, and I think Dayal is here, so he can help answer questions in case I don't know the answers. Okay, so I'm going to start off with a few slides of just general overview and motivation. So my talk is centered on optimization dynamics. I think this is a topic that, particularly in this collaboration, we haven't heard too much about. But I do want to emphasize that there are many important open questions in understanding optimization for deep neural networks. Um, so just let me list a few questions that are on many people's minds. So for example, what makes some optimization algorithms better than others? Like why is Atom W so much better than SGD in some situations? Not all situations, but in some situations. And more recently, there's even newer optimizers that people are excited about, like Muon and Shampoo. It's kind of unclear what's going on with those. A big question that's been around for many years that people are continually working on is what sets the optimal learning rate schedules and optimization hyperparameters. Ideally, one would want to have some schedule and choice of hyperparameters that requires no tuning, sort of automatically just there's some automatic way of doing it, and we don't have that yet. What else can and should we do aside from just minimizing the training loss? Of course, we're interested in many downstream capabilities. Um, so training loss is typically a surrogate, and there's probably a lot of other indications in the training loss of things we could be doing, and we want to take advantage of those, but we don't necessarily always know how exactly. So I'll elaborate more on this point in a few slides. There's an interesting question of hyperparameter transfer as you scale the neural network up to be larger and larger. Um, in some cases, you can have hyperparameter transfer, which is that your optimal learning rate stays the same, or you know how to scale it as you increase the size of the network. But we don't really understand when exactly this happens and why it happens. And just overall, there's many universal phenomena that people have been uncovering over the years. And these universal phenomena give some interesting insight into the geometry of the lost landscape. And it could potentially illuminate how the learning process is actually working and also what kinds of data is learnable and not learnable. Okay, so in our work, our big motivating question actually was we wanted to understand better how to pick the learning rate. So here, we're trying to minimize the training loss, and we have some gradient descent as a very simple example, and the learning rate is the step size that appears here. And obviously, we want to get to a high quality generalizing solution with as few resources as possible. And in convex optimization, there's been decades of work on this, and it's understood how you're supposed to, what kinds of learning rate schedules you should use and how you should pick the optimal learning rate and so on. But in the modern deep learning era, we don't understand this question as well, and it has gained renewed importance and interest. Okay, so one point is that minimizing the training loss is not really the only consideration. There was this famous subject that I think before the LLM era, people were talking about a lot. After the LLM era, it's kind of taken a back seat, although people I know are still interested in this, which is, you might have multiple different minima, but all else equal, there's a suggestion that maybe you should prefer flat minima over sharp minima. Maybe the flat minima generalize better, or maybe they're more robust to perturbations or things like that. So maybe there's other things that we should be having in mind aside from just minimizing the training loss. Um, and there's aspects of the optimization algorithm which dictate what happens aside from just minimizing the training loss. Like the size of the learning rate and the gradient noise play a crucial role in determining the local geometry of the loss landscape. Um, so of course, these neural network loss landscapes are non-convex and high dimensional. So to properly determine the learning rate schedules and hyperparameters, we likely need to better understand the nonlinear dynamics of optimization. And there's, as you'll see in my talk, there's many robust and qualitative and unexpected phenomena that we're still investigating. So one example of this is it seems that larger learning rates pretty much always lead to better generalization, but I don't think it's really clear why. Um, Another one is that this one is to some extent understood, but it's an interesting phenomenon, which is that larger learning rates and noise also bias you to flatter regions of the training loss landscape. Another interesting point is the discussion of scaling laws. So for those of you who are following the literature on scaling laws, there's this notion of optimal compute scaling laws. So you want to find the optimal choice of number of parameters and optimal data set size for a given compute budget. And it turns out that those obey some nice power laws with scaling exponents here. But when OpenAI did this analysis, they came up with some particular choice of scaling, some particular result for the scaling exponents. And then later, Google revisited that and found a completely different set of scaling exponents. And this had a huge impact in industry because following the OpenAI paper, people thought that you should scale the number of parameters much more dramatically than the dataset size. And that led to these huge, huge models that people were training immediately after 2020. And then when this chinchilla paper came out, then they started to realize, oh, we didn't need models that were as big. We weren't doing things properly. And then that sort of led to an era where the models were much smaller. So these things had huge impact on industry. And the reason I'm bringing it up is because in this paper, one of the things that they suggested is the reason that they had a discrepancy, or one reason they potentially had a discrepancy is that is something about the learning rate schedule. Essentially, in this paper, they matched the cosine decay of the learning rate schedule to the number of training tokens, and that was not done in this paper. Now, I actually don't think that's like the main reason why these scaling exponents are different. I have a lot to say about that, but maybe that's a time for another talk. But it's certainly one aspect of the reason why you get different scaling exponents. So all this is to say that this is thinking about the learning rate schedule is extremely important, even if you're just interested in something like scaling laws. The other point, which is actually how we arrived at thinking about this in the first place, is that if you want to understand how neural networks behave as you scale up the system, and as physicists, we're interested in taking thermodynamic limits and so on, as if you want to understand what happens as you increase the scale of the model parameters and the data set size, you need to make sure that you're taking the right kind of limits. And at every scale, you're training the model in a similar way. So, how are we supposed to think about this? How do we define training models similarly at different scales? And this is related to this question of hyperparameter transfer and making sure that we're in the same regime of learning. But then to even define this, we need to think about like, what are the different regimes of learning? Are there different regimes of learning and so on? And so you'll see, hopefully, as I in my talk that what I mean by this different regimes of learning. Okay, so what we're focusing on is sort of looking under the hood and monitoring the local geometry of the loss landscape by simply monitoring the top eigenvalue of the Hessian of the loss. Okay, so this is what we're calling sharpness in this talk. So the most important reason to care about sharpness is that this is what determines the stability of the optimization algorithm and sets the natural scale for the learning rate in SGD. So this is a simple picture that if you have just a quadratic, if the learning rate is less than 2 over the eigenvalue of the Hessian, you converge to the minimum, and if it's larger than that, you'll diverge. And a nice way of thinking about this is that I like is through dimensional analysis. If you think about you have the update equation here, You can say the parameters have dimensions of parameters. The gradient has dimensions of loss over parameters. And so the learning rate has to have dimensions of parameters squared over loss. Whereas the Hessian and its eigenvalue will have dimensions of loss over parameters squared. So there's a dimensionless ratio here, which is the learning rate times the, some property of the Hessian, in this case, the eigenvalue. This thing is dimensionless. So this is the right thing that we should be thinking about, not the learning rate itself. And then the other point, as I mentioned earlier, the sharpness seems to correlate with generalization, at least in some situations. So there was a famous paper by Google, again, before the LLM era, where they looked at a large number of different potential measures of what might correlate well with generalization, and they concluded that measures that are related to sharpness seem to correlate the best with generalization.
Massam, just a quick question on that. I was just before that bullet came up, I was about to ask, why the sharpness rather than something about flat directions or other distributional information about the Hessian. Did that paper sort of explored all of those? Is that what you're saying?
Well,
'Cause
okay, so that paper is talking about sharpness measures. So I guess I should have been more clear. So in my talk, sharpness always means the max eigenvalue of the Hessian,
sure.
but in this paper, I think they were looking at a lot of different things associated with the Hessian. I don't think it was just the top eigenvalue. I'm not even sure they looked at eigenvalue, frankly. I think they looked at properties related to the Hessian, and I don't remember exactly which properties. And you're right to question like what's the best property of the Hessian. Like maybe it's maybe we should be looking at other things like the Frobenius norm or the trace and so on. It's not so clear. Um, so I actually don't, two is not as important for me. I think
Okay.
the most direct thing to really care about in my talk is like we're interested in just kind of things about stability of the optimization and so on. And for that, it really is the top eigenvalue that matters.
Okay. Thanks.
So I have a question about this too, which is I've read in some of the literature from people who are, concerned about alignment that there's this notion that um, that say like regions of landscape that align well would be in some way more complex than those that don't align well. Um, and it's hard to tell whether this is at all justified or where this statement comes from, but you see it said in this literature. Do you have any comments on that? Because
Actually,
the old idea that flatness correlates with good generalization, it makes intuitive sense, but there's, it seems that alignment enthusiasts are concerned that those simple minima are dangerous or, allow the model to take shortcuts or whatever it might be. Do you have any, I'm not advocating this point of view, but I've read it and I wonder if you have any comments about it.
no, I don't. In fact, frankly I haven't heard that actually. So you mean alignments in the sense that Anthropic cares about alignments, like having the model do what you want it to do?
Having the model do what you want it to do. I'm not quoting Anthropic per se. There's just some literature, and there are big organizations that actually Anthropic helps fund too that sort of highlight this notion.
No, that's
So
interesting. I haven't even heard of that statement, so no, I don't really have comments.
okay, no problem. If you want, I can share what I'm
I'd be curious
some
to.
reference, but
Interesting.
yeah, thanks.
Well, actually, one thing that I can say is that Dial has been studying a lot lately, sharpness and what happens during fine tuning. And fine tuning is also how you get the model to align with your preferences. So he might have some actual comments about that, but maybe I'll leave that to him to discuss later.
Okay, great. I'll try to find this and share it in the chat shortly. But yeah, thanks.
Okay, so the main point of my talk really is to explore these figures that I'm showing here. So essentially what I want to get across is that if you monitor this sharpness, top eigenvalue of the Hessian during training, there's typically four regimes of training dynamics that you see as a function of time. Okay, so on the left, I'm showing the training loss. In the middle, I'm showing the sharpness normalized by the sharpness at the start of training. And the right figure is the accuracy, and everything's as a function of time. And so in this particular set of figures, we've picked just a convolutional neural network, but I'll show you shortly that a lot of these things, this is just where this curve is most beautiful, but you kind of see the same basic behavior across many architectures and data sets. So the other point is that I'm gonna be using the parameter C here. So I'm just gonna rescale the learning rate by the sharpness at initialization, and typically be talking about this learning rate constant C. Okay. So when you look at this, you can see that the first regime is this early time behavior, which has a lot of, it looks very transient, it has this transient behavior, and it's in the first roughly 10 steps. And in this early time transient, the loss and sharpness both temporarily destabilize. Then there's this second regime, which is longer, which we call intermediate saturation. So there, the sharpness has kind of found some, it's lowered relative typically to where it started, and it stays relatively flat. And then the training loss is also relatively flat, although this is, log scale. So then there's this third period, which people call progressive sharpening, which actually there's no real explanation of why it happens in the literature, although we're going to have a toy model later that in that toy model we can see why it happens. And then there's this last stage, which is called training at the edge of stability. And that was first pointed out in this paper by Jeremy Cohen and co-authors a few years ago. So that was a convolutional neural network. Here's a fully connected neural network on CFAR10 trained with MSE loss. That also shows these four regimes, although interestingly, it depends on initialization. If for this fully connected network, if we use critical initialization, that's the thing that allows good signal propagation, then you do not see the third and fourth regime. But if you go off criticality, then you do see the third and fourth regime. This is for this fully connected network. Here's the same diagram for ResNets. This is ResNets with no normalization layers. Also, you can see basically the four regimes. Everything I showed you so far was with MSE loss. If you use cross entropy loss, you also see it, although things get a little bit more noisy, but you still see the basic phenomenon. Now, this is all with SGD. So you also kind of see similar things for atom, but you have to look at the right quantity. So a nice way of thinking about atom is as follows. So this is the update equation for atom, where m is the momentum and v is this, is the second moment information. So this is the update equation for atom. And a nice way of thinking about this is that you just have the momentum, but you hit it with this preconditioner. And depending on what kinds of optimization algorithms you pick, you'll have different preconditioners. So atom is, you can think of as having just one particular preconditioner. And if you sort of go into a new coordinate system defined by this preconditioner, then the update equations in the new coordinate system basically look like gradient descent. Okay. So what that means is that we should be looking at the Hessian in this new coordinate system, which is really the preconditioner inverse times the Hessian in the old coordinate system. So basically, this is the thing that we should track to look at something like sharpness for atom. Okay, so the relevant sharpness is this top eigenvalue of P inverse H. And so if you track that top eigenvalue of P inverse H, again, you see kind of similar phenomenon using atom. So this is atom with cross entropy loss. Your sharpness reduces, it kind of saturates for a while, and then it progressive sharpening and edge of stability behavior. This is on language with cross entropy loss. It's much more noisy than the previous curves that I was showing, but you kind of can obviously see the same outlines of the same behavior. So first, let's discuss this early time transient behavior. Here, if the learning rate is below some critical threshold, then it's kind of unremarkable. The loss just comes down, and then the sharpness just comes down. Okay, so both of them are just decreasing monotonically. If the learning rate is above some critical value, but below another critical value, you get what's called this loss catapult, where the loss temporarily destabilizes, it increases, and then it comes back down. And when during that process, the sharpness is dropping much more than it otherwise was doing. Okay, so that's the catapult mechanism. It was just sort of discussed in these two papers. Um, One thing that we found was that if you further increase the learning rate and look at the sharpness, then there's yet another regime where the sharpness also catapults, not just the loss itself, and then settles in at this lower value. And then finally, if the learning rate is beyond some critical amount, then the training just completely diverges. Okay. So let me just show you the simple cartoon for this. Here, this is just gradient descent on a quadratic. If the learning rate is small, you just go down the minimum. If it's a little bit higher, you bounce around, but eventually converge. And if it's too large, then you diverge. This is for a quadratic. But if you take something where you have, say, two basins, one sharper and one flatter, then there can be sort of different critical learning rates. Here you go, if the learning rate is small enough, you'll converge. If the learning rate is beyond some critical amount, you'll actually destabilize in the original sharper basin and then wind up in the flatter basin. And then if the learning rate is beyond some critical amount, you'll diverge. Okay. So actually, if you take this really literally, you'll think, well, when you see this catapult behavior, maybe you're jumping through some kind of barrier. But actually, that's not really what happens usually. If you interpolate the loss if you do some linear interpolation from the starting point to the final point in parameter space, then what happens is that you typically do not see any kind of barrier in the loss. So here I'm just tuning this linear interpolation parameter from 0 to 1, and the loss is just decreasing. It's not increasing as if it's going through a barrier anywhere. Although if you increase the learning rate enough, then you do see the emergence of a barrier. So the picture for that is essentially that the way to think about it is really you have this valley that's opening up, and this is really seems to be an extremely powerful way of thinking about the loss landscape geometry, which is useful in many situations, which is you have this valley that's opening up. And when the learning rate is catapulting, what's happening is that when the network is catapulting, the learning rate is large enough that you're getting this kind of behavior where it's destabilizing, but then it winds up in this flatter region over here. But there's no barrier, because if you just linearly interpolate from where you started to where you're ending, there's no barrier anywhere. However, if you increase the learning rate a lot, you'll eventually wind up somewhere over here, for example. And then if you linearly interpolate, you do see a barrier. So that's essentially what's happening in this setup, where when the learning rate is large enough, you do see a barrier actually show up. But for a small enough learning rate, you see catapult, but there's no barrier. Okay, so that was one point. Then the second point is that the initialization and parameterization of your neural network is extremely important for whether you see this phenomenon or not. So earlier I showed you a fully connected network where, depending on the initialization, you do or do not see the third and fourth regimes. But also you can find other unconventional kind of initializations which start you off in flatter regions, and then you don't see the first regime, and there you start off in progressive sharpening from the very beginning. Okay, so let me try to briefly sketch what that looks like. So there's this standard parameterization for neural networks. And then there's this, what's called the interpolating parameterization. I think this was introduced in Shou's paper, where you kind of have this parameter S that tunes the parameterization of the neural network and also the initialization. And if you set S to 0, that's the standard parameterization. And if you set S to 1, that's this so-called maximal update parameterization that was popularized by Greg Yang. And it turns out that which one, what you pick determines some of this early time dynamics. So if you pick the maximal update parameterization, then the network actually starts off somewhere extremely flat. So meaning the top eigenvalue is very small. And then you just see progressive sharpening and then this edge of stability behavior. Whereas if you do the standard parameterization, you see these kinds of early time transients, you see sharpness reduction or sharpness catapults and then reduction, and then you start to see this progressive sharpening and edge of stability behavior. Okay, so the key lesson here is that this parameterization and the initialization is extremely important for the dynamics. So let me just give you the summary so far of what I've said. So typically there's these four different regimes of training dynamics. Whether you see three and four, or actually one, depends on initialization and learning rates and parameterization. And early time dynamics has a pretty rich phase diagram. Right. Okay. So anyway, I won't repeat this because I just said it. But so this is a summary so far. I just want to maybe to pause and see if there's any questions about anything I've said so far.
I have a quick question. You demonstrated in those experiments that you get this progressive sharpening for mu p, but not for standard parameterization. Do you understand why?
No. So it's not that you don't get it for standard parameterization. It's that for standard parameterization, it shows up later. So for mu
Oh, I
p,
see.
you start off with progressive sharpening from the
Yes.
beginning. Whereas in standard parameterization, you have this sharpness reduction, but eventually you do
Yeah.
see progressive sharpening. So the main point is that you pretty much always see progressive sharpening unless, well, unless you do like in this fully connected network, there was like it's pretty, I would say like almost six situations where you do not see progressive sharpening. In the experiments, progressive sharpening is very, very generic. But what does change a lot depending on initialization and parameterization is whether you start off somewhere really flat, in which case you just start off with progressive sharpening, or whether you start off somewhere really sharp, in which case the first thing that happens is the sharpness decreases, and then you start to get progressive sharpening.
So mu p initializes you somewhere that's closer to the onset of progressive sharpening.
Exactly, yeah.
Thanks.
Yeah, Maissam, I had another question. There's another phenomenon that's a very transient early effect of learning, which is a chaotic phase of learning that lasts a few epochs,
Uh-huh.
which is that if you start two networks close to each other, they'll rapidly diverge
Uh-huh.
early in the training. And my pet theory for that was always that, you're starting high in the loss landscape. It's riddled with saddle points with negative curvature directions. They yield
Mhm.
repulsion, and that's the origin of the chaos.
Yeah.
But here you're sort of only looking at the top eigenvalue. Like, how do you think the rest of the eigenvalue distribution of the Hessian might play a role?
Actually, I will address that, I think, in the next section.
Okay, great.
I'm gonna do some fixed point analysis and a toy model, and then the saddle point will actually be important.
Okay,
But
great.
maybe we can revisit your question after I discuss that.
Sounds good.
Okay, so this brings me to part two, which is this basically trying to understand everything I told you from a simple toy model. Okay, so we want a minimal model that where we can understand the behavior that I showed you, which was quite ubiquitous. So here we're going to study this UV model. The UV model was first introduced, or at least in the modern era. It's just a two-layer linear network with one example, but it was made popular in this paper that Yasaman's also co-author on. But we're doing something, we're adding a little bit of complexity to it, which is that we're considering a more general parameterization for the UV model. So we have this two-layer linear network. We're going to train it on just one example, and then we're going to do this mean squared error loss. And we're going to choose the initialization from this distribution. So then the new thing is really this parameter P. And I'm going to define something called the effective width, which is going to be the width raised to the 1 minus P. And it turns out P is going to play an important role. And really what plays an important role is the effective width as opposed to the width itself. Okay, so if we kind of do the UV model in maybe the way it was first introduced like 5 years ago in that original paper, you basically do not see all four regimes. You'll see the catapult effect, and then you'll see the sharpness kind of just stabilize. So you don't see progressive sharpening or this edge of stability behavior. And that's for the case where you set P to be equal to 0 here, and you take N to be relatively large. Now, if you do something just slightly more complicated, let's take an asymmetric example where instead of like the target Y being at 0, you put it somewhere else, like at 2. Then what you see is, okay, if we keep P to be 0 and we take the width to be large, we again see this, what I just showed you in the last slide. But if we reduce the width, then we start to see this kind of sharpening and then edge of stability oscillation phenomena. Alternatively, if we keep the width large, but change this P to 1, then it turns out that it's more like this maximal update parameterization. And there you also see this sort of sharpening and then edge of stability like behavior. Okay. So basically, you can see all four regimes of the training dynamics if you pick an asymmetric example, meaning Y is not 0, and then you pick a small enough effective width and effective, and you pick a large enough learning rate. Okay, so let's understand what's going on. This is the usual catapult picture that I went through in a previous slide, so I won't describe this again. So to understand this model, you go to function space. In function space, instead of tracking the parameters, you just track, there's only two things you need to track. One is the function update itself. And then here, what I'm calling lambda is actually the trace of the Hessian. Empirically, for this model, the trace of the Hessian essentially exhibits very similar behavior to the top eigenvalue of the Hessian, but the trace is something that we can analytically work with easily. Okay, so the dynamics is basically closes with just these two parameters and these two update equations. And there's effectively three parameters that govern the dynamics. There's a step size and then these two parameters here. Okay, so we're going to analyze this dynamics in the usual kind of physicsy way. So we look at the fixed points of the dynamics, and the fixed points have there's four classes of fixed points. First of all, there's this one, which is a fixed line, actually. That's this line at delta F equals 0. And part of the line is unstable and part of the line is stable. Then we have these fixed points 3 and 4 over here, both of which are unstable fixed points. And then we have this saddle fixed point over here. Okay, and then this line is the line of zero loss because that's when delta F is 0, and that's just going to be that's the residual basically. Okay. Right. So this part is of the fixed line of the zero loss line is stable, and that part's unstable. I already said that. And then the saddle point 2 is actually the point where all parameters are actually 0. Okay, so the usual thing, we have the update map, and then the stability we determine by looking at eigenvalues of the Jacobian at the fixed points. And so the arrows that I'm showing they're not the updates themselves. The arrows are just the unit vector field of function updates. Okay, so just telling you the direction of the update. Okay, so now we can actually try to understand a lot of where this phenomenon is coming from. So the sharpness reduction phenomenon, where the sharpness is decreasing at this intermediate point. The reason that that's happening is because you're attracted to the 0 parameter saddle. So what happens is we typically start off somewhere over here. You're attracted to this saddle point. The saddle point has a lower value of lambda, and that's why this thing is decreasing for a while. Then the intermediate saturation regime, where the sharpness is pretty flat for a while before it starts to do some more interesting stuff, that's because it's passing through the saddle point. It takes some time to pass near the saddle point. That's the intermediate saturation regime. Now, an interesting prediction from this model would then be that if you look, because this saddle point is a saddle point where the parameters are 0, it suggests that as you go towards this saddle point and then away from it, you should see that the weight norm temporarily decreases during this sharpness reduction phase. And we do see some indications of that. It's a very, very minor effect, but we do see that in sort of more complicated networks. Then the progressive sharpening is happening in this picture, basically because you're being repelled from this zero parameter saddle point, and you're being repelled up, which causes the sharpness to increase. Because this is basically a proxy for sharpness here. So it's going up. Okay. So the typical standard initialization will show all four regimes. And that basically is because you wind up starting somewhere here. You're attracted to the zero parameter saddle. That causes the sharpness to reduce, then kind of saturate for a while until it starts to increase. And then if the learning rate is large enough, this zero loss line is unstable and you wind up oscillating back and forth. And that's the edge of stability phenomenon.
Does this model, I forget exactly how it was specified, but does it have the phenomenon of enhanced symmetry, like attraction to enhanced symmetry from the stochastic dynamics? Like this particular saddle is repulsive, but um,
Well, I mean, that's a good question. Here we just have one example, so there's not really a sense of doing like stochastic gradient descent.
okay, you're not that. Okay, that answers it. You're not.
But it might be an interesting point in that, like, maybe if we do many examples and we add the stochasticity, maybe one can see some indications of that phenomena in a similar toy model or something only slightly more complicated.
Yeah,
Um,
there the key issue is a position-dependent diffusion that come if you really modeled SGD. I
mhm,
wonder if that would be an interesting toy extension of the toy model. It's
mhm,
worth discussing, I think.
mhm. Um, okay, so what part of this do I want to say? Right. So there's this critical learning rate because if the learning rate is if it's below this critical amount, it turns out that you have this stable line over here. And so what happens is that the network will come down, repel from the saddle, and just converge to this zero loss line. But if the learning rate is above that critical learning rate, then this zero loss line is completely unstable. So you can never converge to it. The best you can do is just go near it and then just bounce back and forth. So that's the edge of stability phenomena, which only onsets for a large enough learning rate. So this predicts that the edge of stability should only arise above a critical learning rate in particular, which we can also verify in somewhat more complicated networks. Um, the catapult dynamics you can also understand in this picture. At small learning rates, you just initialize close to the stable part of the zero loss line, and you just kind of wind up converging. Whereas at larger learning rates, and also this large effective width, you wind up starting somewhere near the unstable part of the line. And so the gradient updates sort of move you back and forth, and destabilize you until you wind up near the stable part of the line, and then you can finally converge. Now, the interesting thing that happens with the mu p type initialization is that mu p, instead of starting you off somewhere up here, it starts you off very close to the zero parameter saddle. And what that means is just you never have this phenomenon where you start here and you're attracted towards the saddle. You just already start off near the saddle. And so the sharpness already starts off very low, and you immediately just have a progressive sharpening type phenomenon. You immediately just go up from here. So you can understand mu p in this picture as just starting off near the saddle point. Um, and then the interesting point is that as you go up in as you do progressive sharpening, you're attracted to this particular 1D submanifold where the dynamics kind of simplifies and winds up attracted to this 1D attractor manifold, and it just stays on that submanifold, and you just oscillate back and forth. So there's a nice picture for that, which is that let's look at the training as you're going back and forth here. We can project the training onto this 1D submanifold. And when we do that, the loss essentially looks like this kind of Mexican hat type of potential. And if you plot this like a 1D slice of this, it looks like this blue line. And so the point is that it's subquadratic coming from the parameters being zero. So what I mean by that is the dotted dash line is the quadratic, and this thing is flatter away from the minima, and then it's getting sharper and sharper. So basically, the picture that you should have is that the loss landscape has this sub-quadratic nature, at least in this model on one side of the parameter space. And you're approaching it from that side, and that's why you're getting progressive sharpening. As you go towards the minima, the landscape is just becoming sharper and sharper. Then finally, there's this interesting phenomenon of chaos, edge of stability and chaos. So as you increase the learning rates and you monitor the well, okay, here these are the time trajectories. So if we monitor the sharpness as a function of time, sort of late in training, if the learning rate is, in this case 0.54, we see it's bistable, and then as we increase it, we see um, um, kind of like period doubling type behavior, and then as we increase it more, we get even more of these. So you essentially have this like familiar period doubling route to chaos that's happening as you increase the learning rate. And you can also understand that very easily in this toy model because along that 1D attractor manifold, the loss looks like this Mexican type potential. And when you look at the gradient descent dynamics, it's given by this cubic map, which is famously exhibits chaos as you change the parameter. Okay, I briefly mentioned earlier that we had this small prediction for real world networks, which is that sharpness reduction, if it is related to the zero parameter saddle point, you should expect the weight norm to come down as you see sharpness reduction. And that is indeed what you see as sharpness is reducing. Um, the norm is coming down. I actually forgot what, I think this is on a fully connected network. Dial, do you remember what?
This would either be a CNN or a fully connected network experiment. I can't figure out from this level.
Yeah. Anyway, this is like a more real world network, which exhibits this. Okay, so this brings me to the last part of my talk, which is now we're going to take some of the lessons that we learned and apply it to this question of like, why are we warming up the learning rate when we do optimization? And
Actually,
then,
before you get there, your explanation for the progressive sharpening part had a nice 1D flavor to it.
yeah.
If you do sort of principal components in the trajectory during the progressive sharpening, is it confined to very low dimensions? Like, is your 1D explanation essentially the same, the correct explanation for what's happening in higher dimensions?
Um, I think so. Like there was a paper that argued that the reason progressive sharpening is happening is because you have this subquadratic loss, and I think they took a lot of 1D slices. I don't think they did a principal component analysis.
Okay.
We haven't done that. But I think if you take like 1D slices, you do see this kind of subquadratic behavior in real world networks. But we never did that experiment, so
I see.
I'm not that familiar. I should say I do think it's kind of a mystery though in real world networks, like why exactly you see this. I'm not sure. We understood this in this toy model, but I think it's an interesting question to understand it maybe like how much of this really transfers over to real world models, this cartoon.
Okay.
Can I ask a question about the progressive sharpening?
Yeah.
Is there sort of a generic shape of that curve for progressive sharpening? It looked pretty straight, so like a power law, because you were doing a log T.
Oh, you mean like this? You mean
Well,
like
I was thinking more about like in the real world plots that you were showing earlier.
yeah.
Like
Oh, you
it looked
like
pretty, it looked like it had a pretty straight line. So there's some exponent there.
um we never looked at that. Like this
Okay.
was the thing I showed.
Yeah, like whether you know, because like there's a shape and then a transition to a flat, and like what the shape of that curve
That's a good
is.
question. No, I mean, we've never analyzed that. I'm a little hesitant because it's really like in this example, for example, you really see it for one order of magnitude. It's hard to
Mhm.
conclude a particular power law from one order of magnitude. Maybe you can concoct a situation where it's over multiple orders of magnitude. Um,
Mhm.
Maybe
yeah.
I can say something. So progressive sharpening depends on a lot of factors, like what your initialization is, what your learning rate is, and even batch size. So so when you say you want a power law, then I'm not sure
Well,
how
you're
easy.
saying it's only for one order of magnitude, so it's not very power lawy. Yeah.
Well, but that, I mean, I think it is an interesting point that we could be on the lookout for some situations where it's more than an order, it's a few orders of magnitude. Probably one can concoct such situations, or maybe there's some realistic situations where that happens. And then one could try to look at the shape of it a little in more detail. But I don't really have anything to say about that.
Okay. I have an insane speculation, but maybe we can talk about it afterwards.
All right. Okay, so yeah, so the next thing is we wanted to understand better learning rate warm-up. So in modern deep learning schedules, it's extremely common to have this schedule for the learning rate where you basically start off the learning rate at 0, and then you linearly increase it to your target learning rate. And then usually what happens after you get to your target learning rate, then you start to anneal it down to something really small with a cosine schedule, or sometimes you'll keep it constant for a while and then start decaying it. Now, typically the warm-up time is just a few percent of the total training time. In like this Llama 3 model, it was the first 8,000 out of a million steps. So I think it's kind of interesting to think about why you do warm up, what's going on. And there is interest in getting rid of this kind of manually chosen schedule. Ideally, you'd have something where the schedule is kind of like automatically tuned. The network, your algorithm sort of automatically determines it based on some criteria. Um, so there's this North Star of having schedule free learning rates, meaning you don't have to choose anything by hand. And if one aspect of this would be one would need to understand warm up more clearly. Yeah, so some questions. And ultimately, maybe we could even eliminate the need for warm up completely. Like, why are we doing this? Okay, so basically what's happening under the hood, you can get a sense of by monitoring the sharpness. So in the top row, I'm showing standard parameterization. In the bottom row, I'm showing this maximal update parameterization. And so remember in standard parameterization, what happens is that you get a natural sharpness reduction. So the sharpness is just gradually decreasing on its own. But when you do warm up, so here what I'm plotting is um, I'm plotting 2 over the learning rate, 2 over eta. Okay, that's what I'm plotting here. So on a log plot, 2 over eta is just a straight line coming down. So essentially what happens is at some point, the sharpness hits the stability threshold because lambda at some point will surpass 2 over eta. And at that point, you get this kind of dynamical destabilization mechanisms happening, this kind of catapult type effects. The catapult type effects destabilize you and then push the sharpness down further. And then that sort of keeps happening over and over again because you keep increasing the learning rate, meaning you're decreasing 2 over eta. So in standard parameterization, you have this natural sharpness reduction. Like let's look at this orange line. Then at some point you cross this threshold, you collide with it, and then you get a dramatic reduction. And then at some point, maybe you start increasing again, and then you have more collisions. In the maximal update parameterization, you already start off somewhere super flat. So you don't see these kinds of huge collisions, and then dropping down. It kind of gradually increases until much later, in which case you collide with these lines coming down and you destabilize. So the point being that there's 2 regimes here. One is this natural sharpness reduction that you have in the standard parameterization. So the sharpness is already naturally reducing from initialization. You collide with this edge of stability threshold. That induces an extremely strong catapult, causes the sharpness to decrease even faster, forcing it down. And so you get like these one or more isolated catapults until much later, in which case you get like a lot of constant catapults. On the other hand, there's this sort of natural progressive sharpening regime where you're starting off super flat, and there you don't really have a collision with this threshold until much later in training. Okay. So let's see, what am I showing here? So this is the same phenomenon, but with atom. So here we're doing atom, and we're monitoring this P inverse H that I had talked about early on. So again, you see the similar behavior, although interestingly, With Atom, you always get sharpness reduction just from the onset. And I'll actually explain in a moment why you're always getting that for Atom. So for Atom, you always have this natural sharpness reduction and then going up, going progressive sharpening and then colliding back down. Okay, so this is showing the impact of warm-up on training and generalization. So the y-axis is the warm-up time, and the x-axis is the target learning rate. And so the points here is that if you don't do any warm-up, you're down here, you can only tolerate a certain learning rate. And then beyond that, your model just destabilizes and you cannot train it. On the other hand, if you do warm up allows you to tolerate a much larger learning rate. And then that larger learning rate also comes with a better generalization performance. So this one is mu p parameterization with MSE loss. This is standard parameterization with MSE loss. This is mu p with cross entropy loss, standard parameterization with cross entropy loss. Okay, so the main point here is that warm-up is facilitating training at larger learning rates. It's pushing the network into flatter regions. Those regions can tolerate a much larger learning rate. The warm-up time doesn't really, what am I saying here? What was the point? Right, the warm-up time doesn't really matter very much in the sense that like once it's trainable, increasing the warm-up time doesn't really help you very much. What the main point that warm-up time is doing for you is if you're at the edge of trainability, it's allowing you to then tolerate a much larger learning rate. But once it's trainable, increasing the warm-up time more does not really help. And then the lesson being higher target learning rates seem to pretty much always be much better, as long as you stay away from this divergence boundary. If you get too close to the boundary, then obviously you'll degrade. And then the other point is that the reason warm-up is really good is because it makes your hyperparameter tuning much more robust. Because if we say we were not doing warm-up, then we would be like down here, and there would be a smaller selection of good learning rates. Whereas if we do warm-up, we can now tolerate all of these new target learning rates, and many of them are quite good. So you get a larger sort of region of good hyperparameters. So it makes your hyperparameter tuning much more robust.
Mason, I have a quick question.
Yeah.
So said that in MUP you start already from a very flat region, right? Then
Yeah.
how is warm-up actually helping? Can you see that from the picture that you showed earlier?
Well, actually, that kind of showed like mu p is not quite, sorry, for mu, in this case, mu p with cross entropy loss, we're seeing that warm-up is like not quite as important as it was for standard parameterization. So we do see some indications where like if you're doing SGD and mu p, you don't really need the warm-up as much. Although as I showed you with Atom, you are always starting off somewhere sharper. And so you do need the warm-up for Atom. And I'll try to explain more about that in the next slide. Okay, yeah. So here's a deeper discussion of Atom. So one interesting point about Atom, by the way, if you've never really thought about it, is that training never diverges with Atom. With SGD, training diverges, meaning like the parameters are going to infinity. With Atom, that never happens. You get training failure, but it's not because like the gradients are blowing up. It's something else is happening. And I don't have a very good understanding of why Atom fails but does not diverge. I think it's an interesting research question. But this is trained on language, and it's showing us sort of an important benefit of doing warm-up with Atom. So, okay, what did I want to say about this? Oh, okay. So given this understanding, I wanted to give a few little tweaks that one could do that improves the whole warm-up schedule. So a quick one, obviously, is what you start off the learning rate at. So clearly from the pictures that I've shown, it's kind of wasteful to start the learning rate at 0 because you're starting way up here. But what matters is like when the collision happens. So the collision is happening once the learning rate is roughly 2 over the sharpness. So instead of starting the initialization at 0, it actually makes more sense to start the initialization close to this 2 over the sharpness. Okay. Um, so that's like ideally what you would like to do. But of course, you don't want to have to measure sharpness because that's a very expensive thing to do. But here's a nice trick is that you can actually estimate what this sharpness is by looking for when you get the onset of the catapult mechanism. So we did a fun experiment where you just do a line search in the learning rate to see when the loss starts increasing, where you get the catapult effect. And then we use that as a starting point for the learning rates. And that actually gives some savings. In particular, if you were going to do a lot of warm up and your target learning rate was chosen to be pretty small, then you can save all of your warm up steps completely. So this is like a nice little tweak that saves a little bit, although, in some other situations, it's not going to save you too much. So it might not be worth the hassle. Then the second point is, I talked about why Atom seems to always start off somewhere very sharp and always exhibits sharpness reduction. This is like a deficiency of the usual way of initializing with Atom. So basically the point is that um, in Atom, this is the preconditioner. And the way people usually initialize Atom is that they initialize the second moment. Like they would say the second moment at -1 time step is 0, and then at 0 time step would be given by the derivative squared at time 0. And so when you plug this in, you see that um, the the P0 inverse is given by this formula. And basically the point is that at initialization, the gradient has many components that are extremely small. So this P inverse has very, very large diagonal entries, and that causes P inverse H to be huge. And that's what causes the sharpness to start off very high in Atom. So there's a simple tweak to this, which is instead of starting off the second moment like with this, you can just start it off with something slightly different. And then you can improve this in sharpness at initialization by 1 to 2 orders of magnitude. And it turns out that this little tweak actually can completely account for warm up in Atom. So we did an experiment where we did this simple tweak in the initialization, and the benefits of warm up, a lot of them are totally mitigated when you do this very simple principled initialization.
Did you check these things with SOAP or whatever, the thing that's supposed to get rid of the coordinate choice of Atom? Or
No, we haven't looked at SOAP or anything yet. Well, that's an interesting question. The final thing that I just want to leave with is another fun point, which is what I'm calling the persistent catapult warm-up schedule. So what we've seen is that the whole point of warm-up is to induce these like micro catapults and then force the sharpness down. And then allow you to tolerate larger learning rates. That's the whole point. So that suggests that maybe a good schedule is to always just take the learning rate to be slightly larger than that critical learning rate that gives you the catapult effect. So I have some ideas about how you would do that practically without having to actually measure the Hessian, which is what I alluded to earlier, which is kind of you do a line search to see when the catapult is about to onset. And then once you figure that point out, you make your learning rate slightly larger than that. And then that's a good point to have your learning rate at. So we played around with this a little bit. We had some preliminary results, and that's the black curve here. And it turned out that it was pretty nice. Like it was removing these like sharp instabilities that you get during warm up and giving you a nice curve that was comparable to the other ones. But there's a lot of work in actually making this a useful schedule for real world systems. So we haven't gone down that road, but I think it's an interesting thing to think about further. Okay, so that's all I have to say. Thank you.
Ooh, thanks, my son. That was a great talk. We have a little bit of time for questions. Any questions? I guess I can start. What's your sense of the big open problems in this direction next?
Well, like one thing that we're working on is we want to understand hyperparameter transfer better.
Yeah.
So like why the claim to fame with this mu p is why do you is that you get hyperparameter transfer. And it's actually if you go through it, it's not really clear why you should get hyperparameter transfer because the theoretical derivation was for a finite number of time steps in the limit that the width is going to infinity.
Yeah,
Whereas modern networks are in a different regime where you're training for a long period of time compared to the width of the network. But nevertheless, you see hyperparameter transfer work relatively well. So there's like one thing that we're looking at is why do you get hyperparameter transfer to a good approximation in mu p when it doesn't seem to be theoretically very well justified? Um,
I see. I think Cengiz had some work on this on principled hyperparameter transfer, where he used dynamic mean field theory to show that there's a well-defined infinite size limit if you scale things in a certain way.
Yeah, but the issue is that all of those theoretical analyses assume finite time, like
I
order one
see.
time steps in the limit that width is going to infinity.
I see.
Because that's not really the realistic limit. So I think there's like something about the lost landscape that will explain why you still get good hyperparameter transfer. But I feel like that those theoretical derivations are not really sufficient to explain why.
So what would be the realistic limit now? Sort of time being much larger than width.
Yeah, I think time being much larger than width is more realistic.
I see.
Or at least on the same, so let me see. Yeah, the width, yeah,
Or
the
both
time,
of them going to
yeah,
infinity together with a ratio order one.
yeah, something either that or time much larger, actually. I would need to think about it. Probably, I think I need to think about it. Because usually the width is like, a few thousand, and then you're training for like millions of steps. So
Yeah.
it's usually the other limits.
Yeah, that's true. Okay, cool. Um, there's no other questions. Let me stop our
Right.
recording.
So in your
Okay.
toy model, you switched to studying the trace of the Hessian instead of the
Yeah.
largest eigenvalue. Is there any qualitative difference between the results for the trace of the Hessian instead of the largest eigenvalue? Because that's more like the curvature of the lost landscape,
Uh,
especially when you have lots of weights, lots of parameters.
so for real world networks, I'm actually not sure. Dial, do you know, like, does the trace of the Hessian show edge of stability in real world networks? I don't even remember.
The thing is, trace is the sum of all eigenvalues, right? So it's not just the first eigenvalue that's exhibiting progressive sharpening, it's the
Uh,
other eigenvalues as well. So what happens is that your first eigenvalues hit edge of stability, then your trace can still grow because the other eigenvalues are increasing.
mhm.
So they become qualitatively different, but in this toy model, because it's just a two-dimensional model with loss and curvature as the two things. So it's like it's enough to like the curvature, the sharpness, the top eigenvalue, and the trace show very similar behavior.
So it's only because it's a toy model
Yeah,
that these are the same. Okay.
yeah,
But
because there are no other
I
eigenvalues.
think we could say that there are probably some interesting universal phenomena for trace of Hessian, but maybe has not really been studied that
Snow,
close.
you haven't. Yeah. Okay. Thanks.
Right. Any other questions? Cool. All right. Thanks, Maissam.